Hi everyone, this video is the solution for example 1 of the topic of beam moment distribution. So we're going to be solving this simple structure. There's 3 nodes, A, B, and C. A is fixed, B is pinned, and C is also fixed. And between A and B there's a load of 15 kilonewtons. As with everything with the beam moment distribution, we're going to follow these 10 steps so you learn a little bit of everything that needs to be learned on this topic. So as it says here, the first thing we need to do is to lock all indeterminate nodes. In this case, the only indeterminate node we have is node B, because it's the only one that we don't know neither the bending moment that we'll get or the rotation that we'll get. At A and C, we know the rotation, that has to be 0, and therefore they're not indeterminate nodes. The next step then is to calculate fixed tandem moments. So here we only need to know one thing. If there's a fixed bar with a length L and a load F, the moment that we're going to see in the two supports is FL divided by 8. So FL divided by 8. In this particular case, FL over 8 is going to be 15 times 16 divided by 8, which is equal to 30. Next step is calculate distribution factors. And here, the things we need to know is a fixed bar when rotated. So if we apply a rotation, let's say on the left side, it's going to deform more or less like this. But for that, we need to apply a moment, which is 4EI over L times the rotation theta. So let's say that's theta. If we want to apply a certain rotation, we need to multiply by 4EI over L. So in this particular case, we're going to have 2 bars, and we need to figure out the distribution factor in node B. The 2 bars we have are AB, and we have the bar BC. Both of them are fixed because we fixed node B, so both of them will have a stiffness of 4EI over L. In this specific example, the length at AB is 16, and the length at BC is 8. So to get now the distribution factor, so let's do the distribution factor for AB. What we do is the stiffness at AB, let's call it KAB, divided by the sum of the stiffnesses at node B. So what we get for AB is 4EI over 16 divided by 4EI over 16 plus 4EI over 8. The EI simplify, and at the end we get that this is equal to 1 over 3 or 0.333. If we want to know the distribution factor for BC, we can straight away do it 1 minus 1/3, and we know that's 2/3, or alternatively we can do 4EI over 8 divided by, again, the sum of the two. And in this one, again, solution needs to be 2/3. Okay? So that concludes the topic of distribution factors. Next one is carryover factors. And in this case, the only thing we need to know is between 2 fixed supports, there are carryover factors in 2 directions that are equal to 0.5. Now we get to the more complicated step, which is to balance the structure. And here I advise you to draw the structure from the beginning, then make sure you have the distribution factors where you need them. So in this particular case, at node B, we have 1/3 for this bar and 2/3 for this bar, and draw the carryover factors as well, so you don't forget to apply them. The only thing missing now is the fixed tandem moments, and if we look here we have 30, and on the left, because it's counterclockwise, is negative, on the right, because it's clockwise, is positive. So we're going to get here minus 30, and here 30, and then on bar BC, because we don't have any loads, we get 0 and 0. And this is our starting point to balance the structure. Just always remember that this direction, so the clockwise direction, is the positive that we assumed in this method. Now, it's time to balance our structure. So we have here a problem of 30, so we're going to balance, and we're going to make sure we apply minus 30 in this node. And because 1/3 goes to the left, we put minus 10, and 2/3 go to the right, we put plus 20. I mean minus 20. So we are applying minus 30 in total to compensate, and then we distribute according to the distribution factors. And now we can add up, and you'll see here we get 20, and here we have minus 20. So now our node is in equilibrium. The last thing missing is transfer half to each one of the sides. So if you apply minus 20, we transfer minus 10, and here we transfer minus 5. So we can now add and get minus 35, and in this case we get minus 10. Our structure is now balanced, and we can start thinking about the bending moment diagram. To do so, the next step is to calculate free end moments, and this step is very similar to the first one, where we were trying to calculate the fixed end moment. So, but here you see the supports are fixed, and now the supports will be pinned. So your bar AB should look somewhat like this. Now, in this case, this is very simple to calculate. If we have 15, the reactions will be 7.5 in each side, and then the bending moment diagram will kind of look like this, where this moment here is going to be 7.5 times 8, or if you want an equation to always remember, is PL over 4. And in this case, this is equal to 60. So you can do 7.5 times 8, being 8, this distance here, or you can do PL over 4. So we have everything we need, so now we can start calculating our bending moment diagram. I'm going to do it here on this side now. So I'm just going to draw my structure, and now I'm going to put the moments that I get from this table. So I'm going to do the moments from the table here, that after I balance the structure. So I know I have minus 35 here on the left. Again, minus means that is counterclockwise, which also means minus in the bending moment diagram. So here we have to pay attention that the convention for bending moment diagrams is this one. So on the left, clockwise, and on the right, counterclockwise, to cause tension on the bottom, or if you want a smiling structure, okay? Now, on the left side, negative stays negative. So I know that minus 35 will still be minus 35 in my final bending moment diagram. Now, this 20 here, 20 means it's positive. So it looks like this. But a moment like this, according to the definition of bending moment diagram, it's actually negative. So a good mnemonic here is to say, if we're on the left side of the beam, well, here and here, we keep the sign. And if we're on the right side of the beam, here and here, we swap the sign. That's a good way to remember. So this plus 20 that we see here is actually negative 20 according to the convention for bending moment diagram. Now we go to this minus 20, which is on the left side of bar BC. And because it's a left side, we keep the sign. So we know these two moments, and for continuity, we know they have to be the same. And they're both equal to minus 20. Now, the minus 10, again, on the right side, if we know minus means counterclockwise, but in the context of moments, it's a positive moment, okay? So that means this will be indeed positive 10. So we now have the edges of our moments. We have the ones on the ends. And now, between B and C, so don't forget this is node B and node C, we don't have any loads. So we can straight away connect these 2 points. And here we get our negative moment, and here we have our positive moment. Now, between A and B, we have some loads. So on top of this moment here of minus 35 to minus 20, that we could connect straight away if we don't have any loads, we need to add this moment of 60 on top of this. So what we're going to do basically is take that triangle and place it on top of these 2 moments here. Okay? Then this is going to be negative, this is going to be positive, this is going to be negative. And what is going to be the value of the moment here in the middle? We know that just due to the free-ended moments, we know it's 60, but now we need to add the moment that we have in this line. That would be the average between these 2 moments. So minus 35 minus 20 get minus 55, so when we divide by 2, we get minus 27.5. So our final moment will be plus 60 minus 27.5, which is equal to 32.5 positive. Okay? So this concludes our bending moment diagram. Let's just draw it in red. Now the next step is to calculate reactions and shear force diagram. We can do it in one go. So to get this step right, we need to isolate the 2 bars, A and B, and the bar BC. Then we're going to put the forces that we have there, and we're going to put the moments that we calculated from the balancing table. So we get minus 35 here at AB, which looks like this. And then we get 20, and again, it's a moment that looks like this. So they're both negative in the context of bending moments. And then we have minus 20 and minus 10. So in this case, minus 20 would look like this. And then minus 10 will also look like that. I'm just going to draw it like this. Okay, so now, how can we get the shear force in these systems? We're basically going to try to solve it for equilibrium. So what we can see here in AB is if we have 15 acting in the middle, we're going to need 7.5 and 7.5 to balance the 15. And now, if we look at the two moments, we have 35 doing counterclockwise and we have 20 doing clockwise. So the 35 wins and the counterclockwise wins. So our reactions need to do some sort of moment that is clockwise. So we know that our reactions need to be down here and up here. So they do a clockwise moment, okay, to help the 20 beat the 35. And then what is the value of that force? So if we have 20 on one side and 35 on the other side, the difference is 15 of the two. And we need to divide by the distance of the two forces, which is 16 meters, which is the span of this bar. This gives us these two forces, which are equal to 0.9375 and 0.9375. Then we can add them up. And here we add them up because they have the same direction. So in the calculator, plus 7.5 gives me 8.44. No need to be very detailed with the forces. And then on the other side is 7.5 minus 0.94. That's equal to 6.56 kilonewtons, always also pointing up. Now let's look into bar BC. Obviously we don't have any load, so we don't need to do this first step of the 7.5. We just have moments that add up to 30. In this case, they both are counterclockwise. So we need to add clockwise reactions. So to do clockwise, we need up on the left and down on the right. And this creates a clockwise moment that will help us fight this counterclockwise moment. And again, the moment will be 30, which is these two added together, because they have the same direction, divided by 8, which again is the span of this beam. This will be equal to 3.75 in both cases. And these are the directions of these shear forces. So now we are in a position to draw our shear force diagram. So let's do the structure once again. And now we know the shear force starts at 844. At 6, on the right side, it will go to negative. Again, remember the convention for shear force is positive on the left like this and down. This is the positive definition, the positive convention for shear force. So we get 844 pointing up because it's on the left, and then this one, it's pointing up, but because it's on the right side, it has to go down. So this is 566. Then if we look at BC, we have 375 up, and here 375 down, which is also positive on this side. So this one we can connect straight away, 3.75. And now we just have to remember that we have a load of 15 in the middle to allow us to close this shear force there. Finally, to do the reactions, we can see the reaction here has to be 844, because it's this reaction that causes this shear force, this bump. The reaction here in the middle is going to have to be 656 plus 375, which is equal to 10.31. And here at the end, we have a reaction that needs to be 375, pointing down, so it bumps the shear force from 375 down to 0. Right, finally, after the shear force, the last step is to get the deflection. So the deflection, let's do it here next to the bending moment diagram, the sketch of the deflection. And basically the only thing we need to know is the diagram is always drawn on the side of tension. So if the diagram is negative, we know that our beam will be unhappy. So we will have tension on the top side. And if it's positive, our beam will be happy. So we'll have tension on the bottom side. So to sketch a deflection, we then draw our structure again, and we try to combine the information from the bending moment diagram with the information of the supports. So we know straight away that if we have a fixed support here, our beam has to be no rotation and no displacement, and the same applies here at C. And at B, because it's a pin support, we know that it has to go through that point, although the rotation doesn't have to be 0. Okay, so we know this is flat, and we know that it starts to be unhappy, so the beam has to bend down. And when we get to this point that the bending moment changes, the curvature will also change to a happy beam, so something that has tension on the bottom side. Again, when it gets to that point, it needs to flip again, so this is what it would look, and it will be negative until we get to this point here, so something that would have to look like this. And finally, this will flip down a beam with tension on the bottom. This deflection, with a little bit of practice, you can draw it straight away and sketch it just like this. You don't need to know the values of the displacements, but it's important to know that this structure will have to deform like what this drawing is telling us. Okay? So thank you for watching and have a good day.